things. Obviously, we talked about grams to moles, right? And remember that the conversion factor that we use to go from grams to moles is really the molar mass. And we get the molar mass from the periodic table. And molar mass always has units of grams per mole. And we really could use it as a conversion factor to really do either of those conversions, go from grams to moles, or backwards there, go from moles back to grams. And we use it, the number always stays with the grams part, and it's always 1 mole. So you could use it like that, or moles up on top and grams on the bottom. And we get that really from the periodic table. So if you looked at something like carbon, it said 12.01. We could pull it off 4 significant figures and say for carbon's molar mass is 12.01 grams per mole, which again, we could use as a conversion factor to go this way, or for example, this way here. The other thing we talked about as well is Avogadro's number. And Avogadro's number is 1 mole of anything. 6.022 times 10 to the 23. These could be atoms, they could be molecules, kind of depending on the situation. Once again, Avogadro's number is our conversion factor to go really between moles and atoms, are molecules, and backwards, basically, molecules. And once again, that is sort of a constant number, so you always have that number, even though it may not be given to you. But 6.022 times 10 to the 23 atoms per mole, or you could use it, a mole is 6.022 times 10 to the 23 atoms. So remember that you don't want to use Avogadro's number unless there's some mention of atoms or molecules or something like that. If not, then you really shouldn't be using Avogadro's number. Molar mass, again, is used a lot. We also talked about putting that together with balancing equations and stoichiometry. And from a balanced equation, we can take the coefficients, and these are what are referred to as the mole to mole relationship. And it really is nothing more than just the actual number that's there from the balanced equation. So nothing really to calculate other than you're just going to kind of pull the numbers out. For example, we could say for every 2 moles of A we put in there, we get 3 moles of B needs to go in with it. We could say for every 2 moles of A we toss in there, we get 2 moles of C out. And for every 3 moles of B, we get 2 moles of C out. So really, these are all equalities, and they're really just conversion factors that you could use. And from any of these ones, so for example, this one here, we could write 2 conversion factors. We could write that 2 moles of A over 2 moles of C are 2 moles of C over 2 moles of A. The reason we sort of use stoichiometry is in these type of problems, we are typically given information about something we're not interested in the actual equation, and we need a way to convert from whatever they gave us information about to something else in the equation. And that's what the stoichiometry does. Again, it's really nothing more than a conversion factor. Instead of looking it up in a table, you actually use the balanced equation as sort of your place to get your conversion factor to do so. When we do stoichiometry problems, there's really 4 basic steps that we follow. The first step always in a stoichiometry problem is you got to make sure that the equation is balanced. So 100% of the time it needs to be balanced, otherwise it will not work out correctly. The next thing you want to do is take whatever they give you and convert it to moles. And again, a lot of times that is the grams to moles conversion that you would do. And once again, it is the molar mass from the periodic table that would allow you to do that conversion. The reason you have to do that is for the third step, which is the mole to mole step. So you go to the balanced equation and you find the 2 things you're interested in. One thing is whatever they gave you. The other thing is what you're trying to find. Those are the 2 things you're basically interested in. And you come up with that mole to mole relationship. Step 4, you maybe have to do sometimes, and sometimes you might not, but step 4 is to convert the units of moles to some other units. So once again, here on the back end of the calculation, sometimes we go from moles to grams. It's a common calculation, and you need to use the molar mass. Any questions on any of those things there? All right, so let's just say we had this equation here. Let's say we produced 23.5 grams of NH3. How many grams of H2 did we start with? All right, so why don't you take a second or two and give it a try. I want to give you some numbers that might be helpful. Periodic table, nitrogen is 1401, and hydrogen is 1.008. Follow these 4 steps. Remember, start at the beginning and just keep following through the steps and see what you end up with. I'll do it as well. Hopefully we'll end up the same spot. You may look, you just want to follow these 4 steps. So step number 1 is to balance the equation. I see coefficients, so that is done for sure. So we're good there. Step number 2, we want to take whatever they gave us, which in this case is this here, 23.5 grams of NH3, and we want to convert it to moles. So we do need to do that step. So step number 2, we do need to do. We need to go to the periodic table and get the molar mass here of NH3, and that is 1 nitrogen at 1401. And there are 3 hydrogens at 1.008 each. And again, those numbers come from the periodic table. Underneath the symbols is where we get that. And if we add that together there, that gives us a molar mass for NH3 of 17.03 grams per mole, which again is basically what we're going to use as a conversion factor. So we'll start our second part of the calculation here by taking what they gave us, and we're going to convert it into moles using the molar mass. And in this case, we want the grams on the bottom so that they cancel. So we're essentially dividing by the grams per mole of NH3. And if we get an answer at this point, you're looking at something like 1.3799 moles of NH3. So that is the second step here. Any questions on that there? The reason we really need to do that second step is really just to put it in the correct units, which are moles. Now we could do step 3, which is the mole to mole relationship. And this is really the stoichiometry part. So we're going to go to the equation, find the 2 things we're interested in. One thing we're interested in is what they gave us, which is this guy. And the other thing we're interested in is what we're trying to find, which is this guy. And we're going to find the mole to mole relationship here to let us do that. And it really is nothing more than just the actual numbers that are there in the balanced equation. So step number 3 here from the equation, we see that for every 3 moles of H2 I put in there, which is this number right there, I get out 2 moles of NH3, which is this number right here. Again, that's basically where we're getting those numbers from. That's going to give us really 2 conversion factors. That's going to give us 3 moles of H2 over 2 moles of NH3, or 2 moles of NH3 over 3 moles here of H2. So our next step is really we need to go from NH3 to H2. So we want to get rid of NH3 here. So we will take our number from the previous step, which is 1.3799 moles of NH3. We'll use our equation there to allow us to go from NH3 to H2, which means we do need to use the conversion factor here on the left, so everything cancels out correctly. That gives us 3 moles of H2 up on top and 2 moles of NH3 on the bottom. That again comes from the equation. That is the big stoichiometry part right there. That is going to get rid of our moles of NH3. And we are going to get times 3 divided by 2. And if we get a number, bless you at this point, 2.0699, we'll call it, moles of H2. That is step number 3 done here. Any questions on that step? Do I need to do step number 4 here? The answer is I do, because I want grams, right? Right now I'm in moles. So here we do need to do step number 4, which means I do need the molar mass here of my H2. And it is important to remember that you just did the stoichiometry steps, so you are no longer with NH3, you are now at H2. So once again, you need to go back to the periodic table and get the molar mass of H2. And if we do that for H2, it is 2 times 1.008 grams per mole. And it gives us something like 2.016 grams per mole would be, again, the molar mass here of H2. That is what we're going to use. That's really our final conversion to go from moles to grams. And if we do that there, we'll just continue on with step number 4 right there. We'll kind of use the space. We're going to multiply by the 2.16 grams per mole of H2. The moles will cancel, and that will get us 4.17 grams of H2, I believe, we're required. Any questions on any of those steps? Yeah. Yeah. Yeah, so I think I understand your question. It's a good question, and you could do stoichiometry between anybody. So you could stay on the left-hand side of the arrow and do it between those two. You could do it on the right-hand side of the arrow between guys on the right-hand side, or you could cross over the arrow. So you don't always have to cross over the arrow in the stoichiometry problem. For example, we could have been given something like 23.5 grams of N2 and wanted to know how much H2 it was, and you would do the same thing. So you don't always have to cross over. So sometimes people think you gotta go always kind of left to right, and when you're doing it, you don't. But you can go left to right, and you could start at the right-hand side like we did in this problem, go to the left-hand side, or you can stay on either side and do the relationship. That's why in this particular equation or the previous one, there was 3 different relationships you could get, and that's for everybody. So that's what you do. Yeah. Other questions? Questions? No? Yeah. All right. So now that you're professionals, let's try another one here. How many grams of H2 would we get using this equation here, which I think is the one we used last time, but a little different problem. Once again, lithium here is 6.941, bless you, and hydrogen 1.008. All right, we're going to follow our 4 steps. So step number 1 is balance the equation, which is already done for us. So that's good. Step number 2 is convert to moles. And in this case, we do need to do that. So the only number they gave us was 81.75 grams of lithium, it looks like 75 grams of lithium. So to do that, we would go to the periodic table here, look up lithium, and that would give us the molar mass of lithium as 6.941 grams per mole. That is what we're going to use as our conversion factor here. So putting the grams of lithium on the bottom so that they cancel gets us a number at this point. If you did get a number, which would be approximately 11.7778 moles of lithium. Step number 3 is to go to the equation and find the mole to mole relationship. And in this particular case, again, we're looking for the two things that we are interested in. And one thing that we're interested in is what they gave us, which was lithium here. So we're interested in this guy. And we're obviously interested in our H2 there. So from the actual balanced equation, which is nothing more than the coefficients, we could see for every 2 moles of lithium we toss in there, which again is that coefficient, we get out 1 mole of H2, which once again is the coefficient here in front. That gives us our 2 conversion factors we could use, 2 moles of lithium to 1 mole of H2, or 1 mole of H2 to 2 moles of lithium. In this case, we want to get rid of lithium because we ultimately want to get to H2. So that is what we're going to do here. So picking up with the number we had on the previous step, 11.7778 moles of lithium. Using our stoichiometry from the equation, the coefficients, we will use the conversion factor like that. Put the 2 moles of lithium on the bottom, the 1 mole of H2 up on top so that the moles of lithium cancel. We're basically dividing by 2 at this point, giving us 5.8889 moles of H2. And that would then be the third step here. Any questions up to that point? Lastly, here, we do need to go the very last step because we are interested in grams. If we were, again, interested in moles, we would be done. You could put a box over it, maybe clean up some sig figs, but here we are looking for grams. So we will do our moles to grams step, which will require the molar mass of H2 at this point, since we just converted over to H2. Again, from the periodic table, 2 times 1.008, going to give us 2.016 grams per mole. So finishing up here with our number from above, we now are just really doing a conversion of units to grams. So taking moles to grams here. Moles will cancel and will yield us about 1187 grams of H2. So what this means is if you did this reaction and you tossed in there 81 grams or so of lithium and everything went perfect, you should get out 11.87 grams of H2 should be produced in this reaction. Any question on any of those steps? Hopefully you can see a pattern developing here that it is like the same 4 steps. Just follow the steps. Yes. Again, a reminder, if something is done for you, you just go forward, right? And don't undo it. But it really is just the same 4 steps over and over. Yeah. Yeah. Where did I get these guys from? Where I get these from? Is that what you're asking? This. Yeah, it comes from the balanced equation, and that's what the stoichiometry is. So let me I think we have it here somewhere, maybe or not. So it comes from just the balanced equation, and it's nothing more than just the coefficients. So in this case, we had 2 lithium plus 2 waters made 2 lithium hydroxide plus H2. In this case, we were interested in this guy, and it's just nothing more than the actual number that comes in front of it. And those represent the moles of each of those. And that's how we came up with the 2 moles of lithium is equal to 1 mole of H2. Remember that they are equal to each other in terms of what's known as stoichiometry. They're not equal to each other in terms of numbers. Obviously, 2 doesn't equal 1, but it's kind of like a proportion. I think we might have talked about last time. you know, if you want to make a dozen cookies, you got to throw so much flour in, right? And so much eggs and all that kind of stuff. So kind of the same idea with this is sort of proportion wise, they're equal to each other in order to allow this reaction to produce whatever it's producing. But again, they're not equal to each other in terms of numbers, but they're considered equal for conversion factor purposes. So other questions? Yeah. All right, here. One more with gusto. Here we go. If 765 grams of C6H12O6 is consumed by the body, how much CO2 would you produce? And we'll go with grams of CO2. And once again here, carbon is 12.01, hydrogen 1.008 from the periodic table, and oxygen is 16. Okay, let's take a look. So once again, we're going to do our 4 steps. We're going to have a balanced equation, which once again, I do see coefficients, so I'm going to feel like nobody's tricking me. So that is done, hopefully. Step number 2, we want to convert to moles. And once again, here we do need to do it. We are starting with 765 grams of this guy here. So that's where we will start. We'll start with getting the molar mass of this guy. So to get the molar mass of this guy, we go to the periodic table and we just add up all the parts. So there are 6 carbons, each at 12.01 grams per mole. There are 12 hydrogens, each at 1.008 grams per mole from the periodic table. And there are 6 oxygens, each at 16 grams per mole, once again from the periodic table. Buck 80.2 perhaps grams per mole there. Yeah. Again, we're going to use that as our conversion factor. I think that's the right number. Yeah. Went with the top of my head there. That's not what I did. 180.15. Yeah, I'm gonna go with 4 significant figures, so I'll go with 180.2. Sounds good. Thank you. So we'll do that conversion there. 765 grams of C6H12O6. Using again the molar mass from the periodic table. That again is really our conversion factor to go from grams to moles or moles to grams, whichever way you're going. In this case, we want the grams to cancel, so we're going to put our number on the bottom there and our moles up on top. And in this case here, 765 divided by 180.2 will give us something like 4.24528 moles of C6H12O6. Just take into a few digits and not round too much along the way here, since we have to continue on with the calculation. At this point, we're going to go to step number 3, which is our really stoichiometry part. It is the mole to mole relationship. And once again, that just comes from the equation as we just talked about. So we obviously were given this guy here, and we are looking for CO2, which is here. And again, we're just going to take the coefficients that are in the equation, and that will give us the correct relationship. So based on the equation, for every 1 mole of our C6H12O6 we toss in there, we get out 6 moles of our CO2. So again, just the coefficients. That is again what's going to give us our 2 conversion factors of 1 mole C6H12O6 over 6 moles of CO2, our 6 moles of CO2 over our 1 mole of C6H12O6. Too many letters. And continuing on here with our number, that means that we will need to use the conversion factor there on the right to make sure it cancels out correctly. That's going to put the CO2 on top, which is what we're looking for. And that will get us our moles of our glucose going away here. So the moles of these guys will cancel. Taking that number, times it by 6 basically gets us something like 25.4717 moles of CO2 at this point. Any questions up to that? We are looking for grams, which means we do need to do the fourth step, which is now going to take our moles back to grams. So the fourth step here, we're going from moles to grams. We once again need now the molar mass of CO2. So the molar mass of CO2 is 1 carbon and 2 oxygens, each at 16 from the periodic table, gives us 4401 grams per mole as the molar mass of CO2. I believe we also talked about it last time, but just a reminder that when you are asked to calculate the molar mass of something, it is just the formula. The 6 here you do not include, yes, so that's a common mistake that people want to do, is include that 6. You don't do that because, frankly, we did it right here, so you don't want to do it twice. So molar mass is always per 1 mole, so it's just simply the formula, regardless of what the coefficient might be in the equation. You just simply go use the formula to the periodic table. So lastly here to finish this up would be 25.4717 moles of CO2 using the molar mass as a conversion factor, 4401 grams per mole of CO2. The moles will cancel, and that will get us some type of number, 1121 grams of CO2. Probably should end up being something like 1120 on some sig fig action based off of this number, which is the only number we have, which is 3 significant figures in this case. Any question on any of those steps or stoichiometry? Again, hopefully you can see it really is just the same 4 steps. Trust the steps, just do the steps. Don't overthink it, just follow the steps. Yeah. And as was the earlier question, which was a good question, again, we did a lot of examples here where we went across the arrow, but you do not need to go across the arrow. You can see on the one side or the other side of the arrow, and it's still the same 4 steps. You just have the relationship between the 2 reactants, or you have it between the 2 products. Any questions on any of that there? Yeah. Yes, I believe there should be a worksheet on it. Yeah. Other questions? Okay. Okay, that wraps up this chapter here. So we're off to the next one. Just give me a second here to grab it. Okay, we're off to chapter 8 here about gases. So gases is obviously the state of matter there where everybody has pretty much broken apart from one another. And as they are flying around, there's a number of collisions that occur between the gas molecules and the container. And it is these sort of collisions as they are flying around that creates pressure that we associate with gases. So the greater the number of collisions, the greater the pressure we see. Obviously, the less the number of collisions, the sort of lower the pressure that we get. So it is obviously related to as they're flying around in a container. They usually are obviously in a closed container. They fill it uniformly because they are flying around. They also have a lot of energy, which is why they're able to basically be flying around, because they have broken apart from everybody. A reminder, obviously, that in the solid state, everybody is pretty tight to one another, not really moving around. In the liquid state, still relatively tight to one another, but a little bit more room for movement. But then when we get into the gas phase, again, everybody's really completely broken apart from one another. So let's talk a little bit about substances that exist as gases under normal sort of conditions. When we talked about normal conditions, that's sort of like room temperature conditions, and that usually refers to a pressure of 1 atmosphere, and that's what the ATM stands for. It's a unit of pressure, which is an atmosphere. And typically kind of everyday sort of temperature, or a lot of times sort of table temperatures for tables that you find in books and stuff like that. Normal conditions is considered 25 degrees Celsius. Now, under these sort of normal conditions, ionic compounds do not usually exist as a gas. Ionic compounds are usually solid. And that is because ionic compounds are held together by the electrostatic attraction between basically the positive and negative ion that's coming together. That is pretty much the strongest attraction you could almost get, is like that opposite charge attraction to one another. And to sort of overcome that, it typically doesn't happen. So you could heat the heck out of like an ionic substance like salt. Like if you had some salt water and you evaporate it off the water, like maybe you'll do this week or next week, maybe they used to do those experiments, and you evaporate off the water, you'll be left with just the salt that's left over, and you could heat that thing all day and it won't really go into the gas phase. It will just start to melt, which you don't usually want to do in those experiments, but you continue to heat it until it will just pretty much just start to melt. It will not go into the gas phase. Now, other things, molecular compounds, which are really our guys that are sharing electrons. So a reminder, right, our ionic compounds are guys that are not sharing electrons. There's been a transfer of electrons. Something's become positively charged and negatively charged. But guys that actually share electrons, they are a little bit different. A lot of sort of molecular compounds come as gases like normal, how they are, like carbon monoxide, carbon dioxide, hydrogen chloride gas, that's ammonia, and that's methane. Even a lot of those non-metal sort of diatomic elements like H2, N2, O2, Cl2, F2, these are all gases as well, how they normally come. The majority, though, of molecular compounds are still liquids and solids at room temperature. But the major difference between sort of a covalent or molecular compound and an ionic compound is it is a lot easier to convert usually a molecular compound into a gas than it is to try to convert a ionic compound into gas. And that is because when you have, say, something like two molecular compounds, they are held together by what are referred to as intermolecular forces. And these intermolecular forces are relatively strong, but they're not as strong as what is referred to as intramolecular forces, which are basically the forces that hold one molecule together as opposed to two separate molecules. So for example, if we had two water molecules, it is a polar molecule, right? Oxygen is more negative, hydrogen is more positive. When you get two water molecules together, what happens is the negative side of one is attracted to the positive side of the other, and that is what is known as an intermolecular force, the force that holds one water molecule together with another water molecule. And by the way, that force is what is referred to as hydrogen bonding, is the name of that force that holds that together. Now, that is different than if you just took one individual water molecule. The oxygen-hydrogen bond or the other oxygen-hydrogen bond, those are what are known as intramolecular force within the molecule. So within each individual water molecule, there are two forces that hold, basically the bonds is what the force that holds that one molecule together. And that is always a lot stronger than any intermolecular force you could have, because we know that happens because when we start to heat water, it is actually this bond that breaks between the two water molecules, allowing that water molecule and that water molecule to separate. If it was the opposite and these bonds broke, you would produce hydrogen gas and oxygen gas. And if you were boiling water to make pasta, you would never get to the pasta part at that point because you just made hydrogen gas and oxygen gas, but it might explode. So we know just from a simple example like that, that this force here that actually holds the entire molecule together with another entire molecule is much weaker than the force within individual molecules. And so that's why covalent compounds or molecular compounds are much easier to convert into gas, because like all you need is some fire, right? Get 100 degrees and you got water basically going from liquid water to gas. That's what steam is, right? You're basically breaking all the water bonds from each other. Any questions on that there? So the general rule is kind of the stronger the force that holds one molecule together with another, the less likely it will be a gas under normal conditions. And really the weaker sort of force that holds two molecules together is much greater chance that it would be a gas. That's why as we get into organic chemistry, a lot of those guys are gases like methane, propane, butane. They're held together by super weak forces, which means it doesn't take a lot to convince them to go into a gas, which is why when you light your Bunsen burner, gas comes out, right? Your propane tank at home, when you turn the barbecue on, all those kind of things, they're all gases because they're actually held together by very, very weak forces. We'll talk more about those forces in a later chapter, but let's talk a little bit about substances found as gases. So as I mentioned before, a lot of our diatomic elements are going to be gases. So hydrogen, nitrogen, oxygen, chlorine, and fluorine. Ozone is also a gas found in the atmosphere, also why we put sunblock on so we don't get too burnt. Group 8 on the periodic table, those are our noble gases. Those are what are referred to as being monoatomic, which means they come as ones. So like helium, neon, argon, and so forth. They just come as basically ones here. If we look at the periodic table, we could see where we find these guys. And here you go. So on the periodic table, these guys under normal conditions pretty much are going to be gases. So again, our group 8 and really our diatomic molecules there, our hydrogen, nitrogen, oxygen, and fluorine and chlorine. Bromine and iodine are not really gases. Bromine is kind of like a vapor with a liquid, and iodine as well. So there is a difference between the terminology gas and the terminology vapor. A gas is any substance that under normal conditions is found in the gas state. A vapor, on the other hand, is really any gas form of a substance that normally is found in the liquid state or solid state. So an example of that is what we were just talking about, water. We usually call it water vapor. And that's because water is usually a liquid, but you can't convince it to go into the gas phase. And that's why it's referred to as water vapor usually, not like water gas, because it kind of sounds funny too when you say water gas, but usually water vapor is what we refer to. Again, something like H2, N2, any of those guys, CO2, those guys are referred to as a gas because that is, again, normally how they are found. Any questions on that there? So one way that we measure pressure is through the use of a barometer. Old time barometers used to be a pool of mercury with like a glass tube in it. And as the atmospheric pressure would sort of come down on all this mercury, the mercury in the tube would rise. Actually has an inverse meniscus, actually it would go upward. And you would read the barometer from the upwards meniscus with mercury. Nowadays, I think they've taken it out of most schools because it's mercury, so they don't let you use those, I don't think. Maybe you still have one upstairs, I don't know. But now sometimes alcohol electronic type barometers are sometimes used, but a traditional barometer is basically that. A couple of really important units is an atmosphere, an ATM, a torr, which is named after a guy here that invented the barometer, and mmHg is millimeters of mercury. And that is because, again, a barometer here used to have mercury, and frankly, they had a ruler on the side of it, and you basically read the ruler as to where the mercury was. The ruler is a lot of times in inches, centimeters are millimeters. So that is what that refers to, is basically like reading a ruler of where the mercury is. mmHg are millimeters of mercury, and a torr is equivalent to each other. So is a 1-to-1 conversion. So if you had 785 torr, you would have 785 millimeters of mercury. It's an exact 1-to-1 conversion between them. The important relationship here is 1 atmosphere is 760 millimeters of mercury, and that equals 760 torr. That means 760 is your important number to do some conversions. If you have atmospheres and want either millimeters of mercury or torr, you're going to multiply by the 760. And that will give you millimeters of mercury or torr, which again is basically the same thing. If you have either millimeters of mercury, again, or torr, you're going to divide by the 760. And again, that would be millimeters of mercury, or torr. And that would be 1 atmosphere. Those guys would cancel, and that would leave you with atmospheres. So 760, they're going to multiply or divide, depending on sort of what unit you're going with. There are other pressure units, but we really don't get into too many other ones here, but things like pascals, kilopascals, or other sort of units. So kilopascals, pascals, a bar is another unit of pressure. PSI, which is pounds per square inch, is also another common unit of pressure. But for us in this class, these are the 3 really units that we will see the most: atmospheres, millimeters of mercury, and torr. Any questions on that there? Yeah. No, I'm just in this example. I mean, you can use one or the other. Yeah. So yeah, you wouldn't put it in parentheses, but so I didn't have to write it 2 times. They're basically the same thing. So either you could use millimeters of mercury on both of those, or torr on both of them, but you don't need to write them both. Yeah. Other questions? So here's a prettier picture of barometer. Again, a pool of mercury, and as you mentioned, kind of have this inverse meniscus that happens. And again, you basically take a reading of how high the mercury is going there. So when we talk about gas laws, there's really 3 sort of variables we talk about a lot, which is pressure, volume, and temperature. So these are 3 sort of variables that we come across a lot in gas laws. And we're going to see a number of gas laws where maybe we keep one thing constant while basically changing a couple of other things, or we may change all 3 of them together. But these are the 3 sort of common units that we do see. So the first gas law here is Boyle's law. And Boyle's law looks at the relationship of pressure and volume, and we're holding constant temperature. So this is a case where temperature is held constant, but we're looking at changes in pressure and volume. And Boyle's law is basically P1 times V1 is equal to P2 times V2. P1 and P2 is the pressure. It could be any unit you want. It could be atmospheres, it could be millimeters of mercury, it could be torr, whatever unit. As long as they are both the same on both sides, you're okay. Volume is any volume you want. Milliliters and liters are most common. And once again, as long as they're the same on both sides, you're good. You can use any unit you want. Again, as long as they are the same. You obviously would be solving for whatever you're looking for. So what is the relationship here? There is a relationship that when we talk about gases, and if I have a gas and I decide that my gas molecules here, I'm going to decrease the volume. That means all my gas molecules are now in this little spot right here. Would I expect more or less collisions to occur? Everybody's in a really small place. There's a pretty good chance people are going to start bumping into each other, right? A little bit more. And we would expect an increase in collisions, and we would also expect an increase in pressure to occur, right? Now, if I take the same gas molecules and I decide we'll give everybody a little bit more room to move around in, at this point, it's going to take longer for everybody to have collisions because they got a lot more space to fly around in. And what that's going to do to the pressure is going to lower the number of collisions, and the pressure will start to come down. So the relationship in Boyle's law is as the volume goes up, the pressure goes down, an inverse relationship. As one goes up, the other comes down. And as the volume goes down, everybody's in a really small space, going to be a lot more collisions and a lot more pressure that's going to occur. And we start to see a rise in the pressure. It's really good to understand the relationship so that when you do the math, you can make sure your number kind of makes sense, that you didn't maybe do the math wrong. By the way, the other thing is we're going to see a number of gas laws where there is an equal sign. Yeah. And maybe like a fraction situation. And whenever we're crossing over from one side to the next, everybody ends up in opposite locations, right? So You know, if he has to move something from one side to the other, everybody ends up in opposite locations. Even something like this is not a fraction. They're basically both up on top. Yeah. So if you move them to the other side, they end up on the bottom and you need to rearrange it. So that's what we see here. If we look at the pressure here, it is much higher at a smaller pressure, smaller volume. And the pressure really starts to decrease at a larger volume. Again, more room for everybody to fly around, going to limit the number of collisions, and the smaller volume, much more collisions and much higher pressure occurs. So let's take a look at one here and give it a try. We have an inflated balloon, has a volume of 0.55 liters at 1 atmosphere, rises to 6.5 kilometers, where the pressure is 0.4 atmospheres. Assuming the temperature remains constant, what is the final volume of the balloon? So let's see what you come up with here. Doing gas law problems is to really pull out the information from the problem. And if you label it, you pretty much could probably pick the right gas law. So here we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless information in this case. We have a pressure that is 0.4 atmospheres. And we are looking for a volume. If you use it, I'm interested how you use it, but it is, you shouldn't use it. So in this case, if you just look at, obviously we only have one to choose from at this point, which is Boyle's law. And that again is our P1V1. P1V1 equals P2V2. In this case, you could just call the first ones ones if you want, second ones twos. It doesn't really matter as long as you keep the numbers together that go together. In terms of units, we're okay here with the pressure. They're both in atmospheres. The volume here is in liters, which means when we do solve for volume, it will also be in liters. So here we have our P1V1 equals P2V2. We are looking for V2, which means we need to send P2 to the opposite side on the bottom, basically, since it's on the top here. And that would give us P1V1 P2 is equal to V2. So again, if you go across the equal sign, it ends up in the opposite location. We're essentially dividing by P2 is what we're doing here. We're dividing P2 to both sides. And when you do that, those guys cancel and P2 ends up basically over here. At this point, we just want to put in our numbers in the correct spots. So our P1 is 1 atmosphere. Our V1 is 0.55 liters, and our P2 is 0.4 atmospheres. The atmospheres here will cancel. We're basically taking 0.55 times 1 and then divided by 0.4 gets us a 1.4 liters as our answer. Any questions on that there? So if we think about sort of the relationship of Boyle's law, we saw that in this case, the pressure went from 1 to 0.4, which meant the pressure went down, means the volume should go up. And it went from 0.55 to 1.4. So it did move in the correct direction. It's a good way, again, to check yourself that you didn't maybe invert a number or something like that. At least you're going in the correct direction based on what Boyle's law tells you. Any questions on that there? Okay. The next sort of relationship we're going to talk about is Charles' law and Guy Lusik's law. Let's come back. Now, Charles' law, he dealt with volume. He dealt with volume and temperature, and he kept pressure constant. And what he saw was as the volume went up, so did the temperature, and the volume went down, so did the temperature as well. And that relationship also goes with Guy Lusik's relationship, which is he dealt with pressure and temperature, which is very similar, and he held basically volume constant. So Charles' law is V1 over T1 is equal to V2 over T2. Guy-Lussac's law is a similar one. P1 over T1 is equal to P2 over T2. And this is at constant volume. So let's talk about what happens in each of these situations. We'll start with our Guy-Lussac's, which is this guy here. If I have a constant volume for my container, which means it is not going to move. If I increase the temperature in this case, will my gas molecules move faster or slower? They're going to move faster, which means there's going to be a lot more collisions going to occur, right? And that's why we will see the pressure go up, because the volume is fixed, nothing's adjusting, they only got so much room, and they're going to be moving around a lot faster. If I do the opposite and I lower the temperature in this situation where I have a fixed volume, my gas molecules will then be moving a lot slower, right? And as they move slower, it's going to take longer for collisions to sort of occur. And that's going to mean that the pressure actually is going to go down. So in this situation here to the right, as the temperature goes up, because the volume isn't moving, we're going to have more collisions and the pressure will go up, and vice versa. If you lower the temperature, everybody's moving slower, going to take longer for collisions to occur, pressure will start to come down. Now that's a little different than what happens with Charles' law here on the left, or the bottom, whichever way you want to go with it. Now, if I have my guy here with my volume and my gas molecules, and I increase the temperature, and if my volume doesn't move like we saw over here, we would expect the pressure to start to increase, because again, the volume's not going to move. But in the case of Charles' law, we're keeping constant pressure, which means the only way to keep constant pressure is the volume actually adjusts with the temperature to give everybody more room. So when we increase the temperature in a Charles' law situation, what happens is the volume also increases. And what that does is, even though they're moving around faster, they have a much larger area to fly around in. And what that ends up doing is keeping the number of collisions constant. And because it keeps the number of collisions constant, it keeps the pressure constant. So the way Charles' law works is the volume adjusts to allow the number of collisions, even if the gas molecules are moving faster, even if they're moving slower, it adjusts in a way that allows the number of collisions to remain the same. And that's what keeps the pressure from going crazy. It keeps the pressure basically the same as well. So as the temperature goes up, the volume will go up with it to adjust. And the same thing will happen if we lower the temperature. Everybody's going to be flying around a lot slower, which again, in this situation would cause the pressure to come down. What happens in a Charles' law situation is the volume drops with it. And as the volume drops with it, what it does is it keeps the number of collisions being relatively constant, and the pressure stays constant as well. So what we see in Charles' law situation, one goes up, the other goes up, one goes down, the other goes down, and that works for both of them as well. Temperature goes up, pressure goes up, temperature goes down, pressure goes down, temperature goes up, volume goes up, and temperature goes up and down, and volume goes down with it. So as they both go in the same direction with Charles' law and sort of Guy-Lussac's law. Any questions on that there? The other really important thing is what they saw was, in terms of volume, it doesn't matter the units, but the temperature does. It needs to be Kelvin for sure. And to convert into Kelvin, temperature in Celsius plus 273 gives us our temperature in Kelvin. Same thing here. Temperature needs to be in Kelvin. It is a pretty safe bet that if you're doing any type of gas law and it has temperature, you need Kelvin. Yeah, so just change it to Kelvin. It needs to be in Kelvin. Even if they give you the temperature in Celsius and ask for the temperature in Celsius, you need to put it into Kelvin when you go into the gas law. And that's because Kelvin recognized this relationship here. If you graph volume versus temperature for any gas you choose, and you take that line all the way back to the temperature axis, they all hit the exact same spot, which is minus 273.15 degrees Celsius. That number looks familiar because that is the number we use to convert to Kelvin. We call this absolute zero because if you convert it to Kelvin, you add 273.15 gives you 0 Kelvin, which is absolute zero. So because of that, you could thank him for having to convert all temperature values into Kelvin. But again, it is a very safe bet that if it is a gas law, temperature needs to be in Kelvin when you go into the equation. Otherwise, you will get the wrong answer. Again, even if they ask for different units on both ends, in the equation, it's got to be Kelvin. Any questions on that there? Okay, we will lay it up there. I think for today, let's talk about a couple of things.